question? Okay. Let me do a little thing. Let's see. Point presentation. No, not this one. Okay. Yeah, we are set. Okay. And let's get back teaching. So, I guess before we start, a bit of announcement. It's already an announcement, but I'll say it again. So, this Wednesday will be the school's birthday, so there will be no class this Wednesday. Okay. And let's keep on going for our chapter 5, which talks about inner product and orthogonal. Okay, so last time for for section 5.1, we talk about what's orthogonal in Rn, okay, and it's defined through this inner product. So we define this inner product between two vectors. We just to take the transpose of one vector and take this matrix multiplication between them. So two vectors being between Rn, we have inner product being this xty, and the sum over Oi and all the coordinates xi, yi. Okay? And from inner product, we define the angle between two vectors, and in particular, we know that when two vectors are orthogonal, two vectors are orthogonal if only if two vectors are orthogonal if only if their inner product is 0. So this xty will be 0. Okay, and today we are going to talk about orthogonal subspaces on Rn. Okay, and here is an example that will talk a lot of properties around it. But basically, this is the example we care most about. So we think about A is n by n matrix, and then we think about what are the null vectors of A. Okay? So if some x is I guess we did null vector is not really a name, but if x is in null space of A, then we have that Ax equal to 0. This is kind of the definition of x being the null subspace. And if you write down the formula here, you see that A is like this thing, is this block here, and x is this vector, and all those equal to 0. Okay? And if you do look at this equation in more detail, so what are all those 0? Those 0 are okay. So now let's keep drawing. So say the first 0 here is maybe use this one. Okay, the first 0 is this row vector times this column vector. Okay, so this is kind of like an inner product between row and column. Okay, and then the second 0. Then the second 0 is second row times this x vector, and all the way to the last 0 is the last row times this x vector. Okay, and so we see that the fact that the end result is all 0 here means that all those row vector inner product with your x vector equal to 0. Okay, and so this is a very important thing we'll study a lot today. Okay, so this 5.2 basically all revolves around this idea. Okay. Although there are also a lot of generalization we build around it, but this is the most important orthogonal subspace we are going to see. That's the row space of a matrix and the null space of a matrix. Okay? And but before we go that, let's do a bit of a correction. Okay. And so what we say is technically a bit true, okay, a bit incorrect. So that's because of technicality. So we have been saying about row vector is orthogonal to the column vector, but technically row vector and the column vector are in different subspace. So technically row vector are not even in Rn. So you cannot say row vectors are orthogonal to your x, because row vectors are not in Rn because they are 1 by n matrix instead of n by 1 matrix. So you need to say the transpose of a row vector is orthogonal to the column vector. Okay? And so the technical then people in this slide will say is we say the column vectors of A transpose, which is just a transpose of those row vectors. Okay? So this is nothing too hard, just make this technically true. and I think we will even just sometimes just say row vector, because we'll kind of overload the name of a row vector and the transpose of the row vector, because you see there is a really natural one-to-one correspondence between vectors in Rn and a vector in this Rn one times n. Just you need to transpose it, but technically in mathematics there are things in different space. Okay, and with that insight in mind, now let's back to this example. Then we see that because of those 0, we see that x is orthogonal to all those rows, or all those columns of A transpose. Okay, and because x is orthogonal to those, then it's easy to check that if you take a linear combination of those, they are also orthogonal to x. Okay, just because the inner product is linear, because it's just a matrix multiplication. So if you have x1 ty equal to 0, x2 ty equal to 0, then some combination of x1 x2 ty also equal to 0. Okay, and then any row vector linear combination of row vector is orthogonal to x. That means anything in the row space of A is orthogonal to x. And here we have more precise notation. So we have y, which is actually a row vector in R of A. Then because y is already a row vector, so y times x equal to 0. Okay, although this is so this is what it means. So anything in the row space of A or column space of AT is orthogonal to x. Okay. And so here is our for all in the row space. But we also see that we didn't choose x to be anything special other than just being the null space. So also anything inside null space will have this everything inside the null space will have this condition. So we see that actually everything inside null space is actually orthogonal to everything inside the row space. Okay. So so that's the most important factor that we want to remember today. So every vector inside the null space of A is orthogonal to the transpose of everything inside the row space of A. So the null space and the row space, they are both n-dimensional vectors. They are both n-dimensional and they are orthogonal. Remember, row vector has a length n here, and the null vector also have a length n here. Okay. Okay. And so this is the thing we'll build a lot talk a lot about. That's null space. Everything inside null space is orthogonal to everything in column space. Okay. Sorry, this I forgot to delete this slide. Okay, and so let's take the first generalization of this fact. So now we have we see an example of two subspace being orthogonal to each other. Okay, excuse me. Let me try to. Hello. I guess it's working. Just not very loud. Let me try to place this a little closer. Okay. Hello. Okay. Anyway, so let's generalize to any subspace inside Rn. For now, we are just talking about spaces in Rn. So we say two subspaces inside Rn are orthogonal to each other. If you just take anything from X and anything from Y, they will be orthogonal to each other. Okay. And we have a notation for this. We write X is orthogonal to Y. And because this vector being orthogonal is a symmetric definition, then this subspace being orthogonal is also a symmetric definition, meaning that if X is we write X perpendicular to Y, then that also means Y is perpendicular to X. Okay, and here we have kind of geometric intuition. So we want two subspace. Say we have two 1D subspace in 2D, and then we think if the subspace look like this, then they are orthogonal. So one of the subspace is this line, another subspace is this line, and if those two lines are orthogonal, then we think those two subspaces are orthogonal. Okay, But if you have one line like this and another line like this, then this angle is not 90 degree, then we think the two subspaces are not orthogonal. Okay, so that's an intuition about orthogonal subspace. And let's see a lot of examples around it. Okay, so let's we have two subspace inside R3, and X is spanned by E1, so X is the x-axis, and Y is spanned by E2, so Y is the y-axis. And let's check that whether they are orthogonal to each other. So everything that inside X can be written in this parameterized form. So it's just alpha times E1, because X is spanned by E1. So it's this alpha 0, 0, and Y is similarly, this is 0, beta 0. Okay. So this is a parameterized way to write anything inside X. This is a parameterized way to write anything inside Y. And then we take their inner product. We see that no matter what alpha and beta you pick, the inner product will be 0, because you have alpha times 0 here and beta times 0 here. And so we know X and Y are orthogonal to each other. Okay, any question about orthogonal subspace? So orthogonal subspace, the definition is pretty natural. It's just the subspace, two subspace where you take any vector between them, they are orthogonal. Okay. Okay, and here is some example that says that your geometric interpretation about orthogonal subspace might be a little flawed. Okay. And yeah, so you think two subspaces are perpendicular and are orthogonal, but if it's in R3, then you need to be a little careful, because if you have the two planes, then actually two planes cannot be orthogonal subspace to each other, even though their normal vector might be orthogonal to each other. Okay. And yeah, so this is the example. So we have the xy plane and the yz plane. They look kind of like this in R3. Okay, so xy plane is this plane here, and it's this horizontal plane, and the yz plane is this vertical plane. So you might think this horizontal plane is orthogonal to this vertical plane, but actually it's not. And we have two counter examples. I think. Easier counter example to see is this thing. Okay, so we can have a vector that's in both xy plane and the yz plane. That's this vector on y-axis. So you think about this 0, 1, 0 vector is both in xy plane and in yz plane. Okay, but this vector is not orthogonal to itself. Okay. So if you take x1 equal to 0, 1, 0, x2 equal to 0, 1, 0, then x1, and we want to check this thing, we want to check x1 t x2, then it's just an inner product of this thing by itself, and it's 1, and so it's the x1 and the x2 inner product is not 0, so this thing doesn't check out. And then here we have a singular example. So we think about the x1 point is this 1, 1, 0 on the xy plane, and the x2 is this 0, 1, 1 on yz plane, and we take inner product, they are 1. And yeah, so the two subspaces are not orthogonal to each other. Okay, so yeah, so be careful about things in R3. So two subspaces, if orthogonal, two planes are basically never, two planes are never orthogonal to each other, because you want everything inside the spaces to be orthogonal to each other. And so if you have these two planes has a non-trivial intersection, they will never be orthogonal to each other. Okay, and yeah, let's see more example in R3. And now we have the actual orthogonal subspace to this xy plane. So if X is this xy plane spanned by E1 and E2, and what's a space subspace that's orthogonal to X? That's a space that's spanned by just E3, so just the z-axis. Okay, so the subspace that's orthogonal to the xy plane is the z-axis, and we can see the calculation check out here. So everything inside the X subspace can be written as this alpha beta 0, just something in xy plane, and everything on the z-axis can be written as this 0, 0 gamma, and we take their inner product is always 0 for any alpha, beta, and gamma. Okay, so you see this xy plane and this z-axis is they are orthogonal to each other. Okay, and yeah. And we also see another thing about this orthogonal subspace to xy plane. Okay, so here we prove that this z-axis is yeah. So this is a kind of another way of direction. So we say z-axis is orthogonal is a subspace orthogonal to x. And we can also show that z-axis is everything that's orthogonal to the xy plane. Okay, so yeah. So now if you want to check what are every vector, so here the important thing is this every vector. Okay. Okay. So here, so its difference is kind of here is sufficient. So in this slide we say z-axis is being on z-axis is a sufficient condition to be orthogonal to xy plane, and here we are thinking about necessary. This is hard. Okay, yeah. So we say that being on z-axis is a necessary condition to. Let me see. Any vector orthogonal to. Oh, I guess it's actually the other way around. But I guess it's okay. I like the other way around, but this is how we taught. Okay. So we say the z-axis is a necessary condition to being orthogonal to x, and we go the other way around, but also. Sorry, this is sufficient. And here we say the xy plane is the necessary condition to be in orthogonal to this is the z-axis. Okay. Yeah. So we want z to be orthogonal to every vector in y. Then z is orthogonal to E3, and we take this thing and we see z3 equal to 0. Okay. And we see that if z3 equals 0, then this is in x. Okay, and yeah, so this xy plane is everything that's orthogonal to y. Okay, and then this orthogonal to everything is another concept that we want to take now. Okay, so yeah, so here we have the definition of orthogonal complement. Okay. And I think this is oh no, there are a lot of well, there are a lot of concepts we don't talk about, but this is I guess the second concept we talk about today is orthogonal complement. So orthogonal complement is a bit of a stronger condition than being orthogonal. Okay, so yeah, let's jump back, compare a little bit. So so the first, the first concept we define today is two space being orthogonal. Okay, and so we give subspace X. There are a lot of subspace that are orthogonal to it. Okay, but orthogonal complement is a unique thing. Okay, so I guess we actually say Y instead of X. So we can say. There can be some x that's orthogonal to y, and there are a lot of x that's orthogonal to y. Okay, but the orthogonal complement is a unique thing. So if given y, then there is a special subspace that's orthogonal to y. That's basically the biggest subspace that's orthogonal to y, and that's orthogonal complement, because it's everything that's orthogonal to y. And yeah, and we write it in this way. So y with y, and with the superscript being this perpendicular sign. Okay, so this y perpendicular is everything inside Rn that's orthogonal to y, and it's called orthogonal complement. And also jumping back, yeah, I guess a bit of a spoiler. we say that everything we talk about today is about this row space and null space, and very soon we'll prove that the null space of any matrix is orthogonal complement of the row space of any matrix. Okay. And yeah, so this is orthogonal complement, and let's see some property about orthogonal complement. Okay, and yeah. And yeah, so first, if two subspaces are orthogonal to each other, they are not necessarily orthogonal complement. Orthogonal complement is a very special subspace that's perpendicular to y. That's orthogonal to y. Okay, and here is a counterexample. So you can have two subspaces in R3, and maybe let's draw a bit of a picture because it's nice to draw a picture in R3. So we have R3 being this XYZ space. Okay, and let's draw the axis a bit better. Okay, XYZ, and we have our X subspace being this X line. So here is X, and Y subspace being this Y line. This is Y. Okay, and they are orthogonal to each other because everything on this X line and everything on this Y line are orthogonal to each other. But Y is not the orthogonal complement to X because Y is not the orthogonal complement to X because there are also things on, say there are things on the axis, or there are actually the orthogonal complement is the YZ plane. Okay, and yeah, so there are something that's also orthogonal on to X but not in Y. Say things on the Z axis is also orthogonal to X, and it's not inside Y, so Y is not the orthogonal complement. Orthogonal complement need to be the biggest subspace that's orthogonal to X. Okay, and yeah, here we have the orthogonal complements, and the orthogonal complement of X is the YZ axis, and the orthogonal complement to Y is the XZ axis. Okay, so here is the idea of orthogonal complement. Okay, and yeah, I guess also a bit of a spoiler, and I think the serial number, yeah, a bit later we'll prove. Let's write this first, but prove later. But it's nice to know this first, and you also kind of see this intuitively. So if you have any subspace, let's say the Y, and you take its orthogonal complement, it's a subspace, then you take the orthogonal complement back, then you go back to your Y. This is one of the theorem we'll prove today. Okay, and yeah, you can see that kind of intuitively here. If you have X and its orthogonal complement is this YZ plane, and then you think about YZ plane, its orthogonal complement is back to this X-axis. Okay, and yeah, so this is orthogonal complement. Any question? Okay, and yeah, then here we have a remark, which is so this first remark, I guess we should really say it as a lemma or theorem, but anyway. So this is kind of our 5.2.0 because we will use this quite a bit of time. Is that if X and Y are orthogonal, then the intersection of X and Y is just a zero vector. It's not an empty set. It's a zero vector. Okay, and we can see a whole bunch of examples already. So just go back here. So you have this X-axis is orthogonal to Y-axis. Then their intersection is just this 0 point. Okay, and we know, yeah. So intersection is you have any two subspace. Then because any subspace must contain a zero vector, so any two subspace must have intersection being this zero vector. And so here we are saying another way to interpret this is that if two subspaces are orthogonal, then their intersection is minimal. It's this zero vector that they must intersect. Okay, and here we have a very quick proof here, which we kind of already see idea. So we have a see idea of this proof in our counter example here. Okay, so if our two subspaces are orthogonal, two subspaces are orthogonal, and we have something that's both in x and y. So this intersection of x and y, then the inner product of it must be 0, because inner product of itself is something in x and something in y, and we think this x, the first. So here we are thinking the first x is in x, and the second x is in big Y, and but we know everything in x and everything in y must have inner product being 0. So x inner product with itself must be 0. So the length of x must be 0, and the only vector with length of x, with length being 0 is just a 0 vector. Okay, so that's a proof of this very nice lemma 5.2.0. Okay, and also we have another theorem here, and I guess we kind of already assume this theorem being true, but yeah, it's very nice to know. Okay, and that's we talk about this orthogonal complement. Already treated as a subspace, but we need to prove this. Okay, so we have a subspace, then orthogonal complement is also a subspace. Okay. And it's quite easy to check. You just need to check. As always, when we want to check a subspace, it's just we need to check closure. Okay, so we need to check that something inside subspace, inside orthogonal complement, is closed under scalar multiplication and under addition. Okay, and yeah, so basically we just check orthogonal is being orthogonal is closed under linear operation. So if something is inside orthogonal complement, then alpha times it, some scalar multiplication of it is also inside orthogonal complement. Okay, and yeah, so we want to check this alpha x is orthogonal to every y inside your y, every small y inside your big Y. So alpha x ty, and then we just use linearity on this matrix multiplication. Then this is alpha times xty, and that's alpha times 0. Then now it's just scalar multiplication is equal to 0. Okay, so alpha x inside y orthogonal, y perpendicular. And also you have two things that in this y perpendicular. Then you also check x1 plus x2 inner product with y is x1 inner product with y plus x2 inner product with y. So this is 0 plus 0 equal to 0. Okay, and yeah, so this orthogonal complement is closed under scalar multiplication and vector addition, and so it's a subspace. Okay, any question about this two ideas? So we talk about orthogonal complement and orthogonal subspaces. And so orthogonal subspace is just two subspaces where every vector inside them are orthogonal to each other. And the orthogonal complement is a special orthogonal subspace. Is the largest orthogonal subspace. Is everything inside this bigger space R that's orthogonal to your starting subspace. Okay, are we all good? If we are good, then we are back to talking about matrices. Okay, and oh, sorry, let me fix my power first. We are a bit low on battery, and okay, let's show this slide. And here we be a bit of trouble because of a notation issue. Okay, it's quite annoying. Yeah, this project is a bit more complicated than necessary because it's a bit hard to get the notation correct. Let me Is this power correct? And okay, we are charging. Okay, and anyway, so now we want to talk about yeah, and yeah, now we want to talk about all those orthogonal subspace ideas around matrices. Okay, so we back to our n by n matrices. And remember, there are all sorts of fundamental subspaces that are around this matrix A. And so there are this column space of A, and row space of A, and null space of A. Okay. And basically, spoiler ahead, we want to say the row space is the orthogonal complement of the null space. Okay. But anyway, let's have a bit of a review on the fundamental subspace. Okay, so A is n by n matrix, and we say, and we can think about column space of A. Column space of A will linear combination of the columns, and it can be also written in this way. So something inside column space, if it's B equal to A times X, where X is something inside Rn. Okay. Because we can think about A times X as you take a linear combination of columns with respect to those numbers X. This is something we talk in chapter 1. Okay. And yeah, and now we think about column space of A, and another interpretation of column space is it can be written. Think of as the range of A. Okay, if you think A as a linear transformation, and here is where we get a bit of a notation trouble. So the column space of A in the book, you actually write this as R of A instead of C of A. But in our slide, we use as a C of A for column space. But in the book, because it's the range of A, remember in chapter 4, we talk about like the kernel and the range of a linear transformation. And yeah, so here is where our notation change a little bit in textbook. This is called R of A, but we have changed it to C of A. But just keep in mind, it's a bit confusing if you read the book. It's a bit different than our slides. Okay. Because the book want to say it's range, but range and row are both called R, and I think it's well, we need to make a decision, and I decide R should be for row instead of range. Okay, and anyway, so the column space is the range of A. Okay. And so weirdly for this range of A, I denote it as a C of A, and yeah, C of A is the column space of A. It's the vector that's equal to A times some whatever X, and this column space of A is in Rn. Yep. And and then we have this column space of AT, which is basically the row space of A, but taking a transpose. Yeah. And we've seen this before because we want to see things inside this column vectors. Okay, so we need to make this weird transpose. And anyway, this we also have this row space of A, which is has a one-to-one correspondence to this column space of AT. Okay, and those are vectors inside Rn. They are vector of n dimension. Okay, so column space is vector of m dimension. Row space is vector of n dimension. Okay, let's draw our matrix a little bit here. So our matrix A here, it has this not matrix here has let's see. So the length of rows are n, and the length of columns are n. Okay, so n by n matrix. Okay, so row vectors has length n. Okay. And to say row space, we actually say column space of A transpose, just because the technical issue. This is a technical issue we already see. Okay. So yeah, so here we have this those space idea we already talked about, but the notation is a bit fuck up. Because of two issues. First is the collision between we want to think about range or think about column. So there's a difference between R of A and C of A, and also the row space. Because it's a row vector instead of column vector, and so we actually take the column space of A transpose. So we have a lot of HR transpose around to make a row space, actually instead of a row vector, column vectors. Okay, so yeah, we have those two issues, but we already know column space and row space, linear combination of rows and a linear combination of columns. We learned that in chapter 3 before midterm. Okay, and yeah, then we go to our fundamental theorem. So this is the thing we want to say. We want to say, I guess this is something we already showed at the beginning. So we see that the null space is perpendicular to this row space, or the column space of A transpose. Okay. And yeah, so this is something we see at the beginning of today. That null space is orthogonal subspace to the row space of A. Okay, and yeah, and this is something we state without proof. And the actual theorem we want to prove is, I guess we can prove in this last 10 minutes of this class, is that null space is not only perpendicular to your column space, it's the orthogonal complement to the column space. Okay, and here we also need to prove something extra because we don't have the complement of complement is also complement. So we also prove that. Sorry, this is the other thing. Okay, so null space is the complement of the row space. And also you can take the transpose of it. So null space of a transpose is a orthogonal complement of this column space. Okay, and let's first prove the first one. The second one is you just take a transpose of A. Okay, null space of A is orthogonal complement of the row space or the column space of AT. Okay? And so there is two things. So first, null space is inside this orthogonal complement, just because null space is orthogonal complement is null space is perpendicular to column space. This is something we state without quite proof, but it's quite easy to see, because everything inside the null space is orthogonal to everything inside the row space. Just let's jump back a little bit. Just this argument we run through. Okay, this argument we run through. Because every row here is orthogonal to everything inside column space. It's orthogonal to everything inside null space, and so any linear combination of rows is orthogonal to everything inside null space. So yeah, everything inside row space is orthogonal to everything inside null space. Okay, and yeah, jump too much. Okay, and this means null space inside is orthogonal complement. Okay. And then the second part of proof, we want to say everything inside orthogonal complement is inside null space. Okay, and yeah, I guess I should highlight the two parts of proof. First part, we want to show this. The second part is want to show this. Okay, and yeah, we start with something that's inside the orthogonal complement, and we want to show it's inside the null space. Okay. And if something inside orthogonal complement of our row space and actually the column space, and so here we be careful. We want to be take care of be careful about being a row vector or column vector. So actually say it's orthogonal complement to this column vector of AT. So think about this AT. It has those columns that's actually rows of A. And we want something that's inside orthogonal complement. That means this thing. Then this x taking transpose must be this x taking transpose and multiply on this AT must be the zero vector, because x is orthogonal to every column here. Okay, this Yeah, so because X is orthogonal to every column here, this is by definition. Yeah, because X is also perpendicular to every column here, and so X transpose multiply on every column must be 0, and then you think about this H transpose multiplying this A transpose is just the result will be a row vector, and each element of this row is just X transpose multiplying every column here, and it should be all 0. Okay, and yeah, so we say a lot, but the end result is just the X transpose multiplying on this N transpose is 0 row vector. Okay, and it's a 0 row vector, so we write this vector sign here. Okay, this should be quite straightforward, but just a bit of notation because we transpose a lot of things around. Okay, so this is this 0 row vector being that is X transpose times A transpose. Okay, and now with this we can forget about how those matrices write up. We can just do this algebraically. So X transpose times N transpose is A times X transpose. Okay, and then we take the transpose of both sides of this equation. Now finally we back to our column vectors. So we have AX being the A times X being the 0 vector. Okay, and this is exactly the definition of X inside the null space of A. Okay, so we see every X that's inside this this orthogonal complement of row space of A is inside the null space. So we know that this orthogonal complement is inside the null space of A. And yeah, so with these two inclusion identity, and I guess here I should technically write this include equal sign to mean that they can be naturally equal. Okay, so with these two property, we know that those two sets are equal. So this C of AT perpendicular is equal to null space of A. Okay, and and yeah, and then the next one we just we just have AT instead of A inside. So we have some B equal to AT. The null surface of AT is null surface of B. That's the orthogonal component of column space of BT, which is just because we have ATT equal to A, and yeah, that's just column space of A and orthogonal complement. Okay. So, but I guess we can have a bit of interpretation of this. So we want to find the orthogonal complement of the column space of A, and that will be the null space of A transpose. Okay, and yeah, finally we have a bit of extra proof that we stayed with just intuition. So we want to prove null space of A is actually perpendicular to column space of AT, or null space of A is actually perpendicular to row space. Then we can have algebraic calculation here. So something inside null space and something inside column space of AT. And they will satisfy those two things, and anything inside null space means A times X equal to 0, and something inside column space of AT means there exists some Z such that Y equal to AT times Z. And yeah, this is how we talk about column space before. And yeah, then now we take an inner product between X and Y. Then we have xty equal to xt. Here we use this y condition here, so equal to xt and atz, and then we can do multiplication between xt at first. That's ax transpose, and then we use ax equal to 0. So this is 0 transpose on times z, but anything inner product with 0 is just 0. So here we prove that anything inside null space and anything inside row space are orthogonal to each other. Okay, with the actual algebraic proof here. Okay, so here is our theorem. So one of the most important theorem, and says that the null space of A is the orthogonal complement. So orthogonal component of the row space of A. Okay, and we can see some examples. So A is this thing, and here we actually prove the second part. So we want to say current space of A and its orthogonal complement is a null space of AT. Okay, so A is this quasi-singular matrix. So it's a current space because one of the column is just 0, 0. So the current space is just a near linear combination of the first column. So just alpha times 1, 1, 2. And yeah, so this is the current space of A. Yeah, and then now we have a null space of AT. So AT is this weird space 1, 2, and 0, 0. And null of AT, then we take just a calculation here. So something x1, x2, want it to be 0, 0. Then we see that 1x1 plus 2x2 must be 0. Okay, and this gives us x1 and x2. I guess let's write down a bit of a middle calculation. So x1 plus 2x2 equal to 0. And so we can pick x2 equal to any beta, and x1 will be minus 2 beta. And so we have the null space being beta times is minus 2, 1. Okay. And yeah, so we take a null space of AT, anything inside null space of AT, inner product with anything inside the current space of A. And we see that it's alpha beta times this minus 2, 1, and 1, 2, and it will be 0. Okay, and yeah, so we check the null space of AT is perpendicular to current space of A. And yeah, but here we haven't proved that they are orthogonal complement, but it's just a bit of checking that they are orthogonal to each other. Okay, so yeah, let's take a 10-minute break. And we will say more things about those orthogonal complement next class.哦，好，谢谢。我看一下，演算法不理想，所以你现在修了，看起来很多。是现在剩哪些啊？我看一下。不对，这是课表吗？
对。
这样子还必修吗？所以演算法是这个，所以这个没有了。
对。
然后所以你还剩1、2、3、4、5、6门课。你还剩这么多课吗？6门课低修，为什么？你是其他也退掉了？
因为这样剩就是只有2而已，他这样就是这样。
哦，排球没有算的。OK。好，游戏程式还是蛮多的。OK， 好。都还可以吗？其他课？
目前对，就只有演算法不太行。
OK， 好，
谢谢教授。
Okay. Oh, 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 low better. Anyway, yeah, I think it's time to start again. Okay. So yeah, let's talk more property about orthogonal complement. Okay. Now we have two very important theorems to prove, and here we just write a little bit. So that's the very nice intuition about orthogonal complement is that, remember, with the orthogonal complement of a subspace is the biggest subspace that's orthogonal to it. And actually, because this S perpendicular is the biggest subspace, so those two subspace together kind of fill up Rn. Okay. Although the fill up doesn't mean that the intersection is Rn, they fill up in a kind of weird sense that we'll talk about very soon. Okay. But let's first see this theorem. Okay. And basically, the two spaces themselves don't fill up Rn, but their bases fill up Rn. Okay, and yeah, the first is this theorem here. We say that So if you add the dimension together, there will be n. Okay, so you want this is a n-dimensional space, and so you add those dimensions together, you will become n. And also you have a basis for S and another basis for, you pick any basis for S and any basis for S perpendicular, and just list those bases together, you will also become a basis, and it's a basis for n. Okay. So here the important thing is we have a basis here. Okay, basis, basis, and basis. Okay. Any question? Okay. And yeah, so let's first start proving this. I guess we don't finish the whole proof. We left out a little bit, but we have most idea here. Okay, and to prove this, and we want to use a bit of the matrix thing we learned about. Okay, so how we get a matrix out of those things is we think about we make this basis inside a matrix. So we make a matrix that just you take this basis with any order and list them into a matrix. So we have x1, x2 to xr listing together as a matrix, and this will be a n times r matrix. Okay, and okay, and now we think about what's the dimension of S. So S is just the column space of this X matrix. Okay, so now we can express S and S still in terms of this matrix. Okay, and so first we know S is just the column space of this matrix because this is a basis, and everything inside S is a linear combination of those vectors. So the column space of this big X is equal to S, and so you can take the dimension of both of them, and then we want to actually transpose a little bit, so we'll see why we want to do this later. But the column space of X is obviously the row space of X transpose. Okay, and then you take a dimension, so dimension of S equal to dimension of a row space of X transpose. Okay. And then we use our theorem very first. Okay, and so now what is S perpendicular? Now we can use what we have before. So S perpendicular is the so here we use I guess we need to be a little careful. So S perpendicular will be the null space of X transpose. So here we use I guess let's write this down here. Something we just proved is theorem 5.2.1. We say the perpendicular to the column space of X is equal to the null space of X transpose. This is the less obvious example of this theorem. Okay, so we say null space equal to the complement of row space, and we take a transpose. Then we have the null space of A transpose is the complement of column space. Okay, so here we use this. The complement of column space equal to the null space of a transpose, and we change A to X. So we have the complement of the column space equal to the null space of a transpose, and we know column space equal to S. So this complement of column space is just the complement of our starting space S. Okay, so here is a bit of knowing what is what, and in the end we get that this complement of S equal to null space of X transpose. Okay, and then we add a dimension in front of both sides. We have a dimension of S perpendicular equal to dimension of null of xt. Okay, and then we can use something we proved in chapter 3. Okay, now we can use our rank nullarity theorem nicely. Okay, we have dimension of S equal to this thing, and dimension of S perpendicular equal to this thing. Okay, and but those two things they are dimension of the two subspace of X transpose is the dimension of the row space and the dimension of the null space. And we know dimension of a row space plus dimension of null space is just by rank nullarity theorem is just dimension of the dimension of the width of this matrix. And we know xt is X is n by r matrix, and xt is r by n matrix. And yeah, so you do rank nullarity theorem, you will get this n here, which is the number of columns of this xt. Okay, so yeah, so this is quite a technical proof, but we see that with the rank nullarity theorem, we see that because basically S is correspond to some row space, and S perpendicular is some null space, then by rank nullarity theorem, the dimension of them added together will become n. Yeah. And yeah, so this is why rank nullarity theorem is useful. This tells us for every subspace in Rn, the dimension of it plus the dimension of its complement equal to n. Okay. And the next part, we need to prove that you have those two bases, and listing together, you become also a basis. Okay. And yeah, and so because of the first part, we know you have a basis of the S and a basis of S dual, then S perpendicular, then the total number of elements here, it should become n, because this dimension plus this dimension is n. Okay, so we already have n vector here, and to have this being a basis, I guess there are two ways to prove this, because we know we need to have two of the three things. We need to satisfy two of the three properties for this set to be basis. Is either the total number of them being n, we already satisfy this. Then we need to prove either they are linearly independent or they span the whole space to say they are a basis. Okay? And proving they are span actually harder. That's something that we'll prove later. But you need to use this result to prove that they are span. But so here we prove they are linearly independent. Okay. And to prove they are linearly independent, so basically we need to, so here is the part that we kind of skim over. But basically we need to prove, maybe let's go to the next slide. We have a bit more. Let's do it here. So we need to think about this thing, right? We need to check something is the Li. We need to think about what happens. We want to have this dependency equation. So C1x1 plus C2x2 plus plus CRxr, then plus CR plus 1, XR plus 1, plus CNxn equal to 0. Okay, and we want to check whether this thing, when this thing equal to 0, then all the C equal to 0. Okay, and then we see that we have two vectors adding together being 0, and the first part is the first part is inside S, because it is a linear combination of something inside S. So this side is inside S, and this thing is inside S perpendicular. Okay, and let's think about something inside S and something inside S perpendicular, and and then here we actually want to say something extra, and it's a bit of a spoiler to quite a few sections later. Okay, so actually you can say prove that you have two non-zero vector. Two non-zero vector, if they are orthogonal, then they must be linearly independent to each other. Okay, and so we know this vector is inside S, this vector inside S perpendicular. So those two vectors must be orthogonal to each other, and next theorem that we'll prove much later is that if vectors that are orthogonal to each other, then they must also be linearly independent. And quick proof is here. So yeah, so if y and z are orthogonal, then that means y transpose z equal to 0. Then if you want to check c1y plus c2z equal to 0, then you take y transpose on this equation. Then you have that. Oh, sorry. Here I should write this is actually the 0 vector. Okay. So you have y transpose on 0 vector equal to 0, and the other way is c1 y transpose y equals 0, but y is non-zero, so this means c1 equals 0. And similarly, you have c equal to 0. Okay, and yeah, so because those two are Li, and so the whole thing must be Li, or but yeah. Okay, so here is actually a more complicated proof than what we have in classroom in the book. So the book actually just say this is y, and yeah, but yeah. Yeah, but I guess easier to prove this is you say this is y, and this is z. Then you have y equal to minus z, and so y and z are both in they are in S, and they are both in S and S perpendicular, and that means y equal to z equal to this 0 vector. Okay, but yeah, here is nice thing to know, and we will talk about this more in section 5.5. So here is a bit of spoiler. In 5.5, we will say every orthogonal, any set of orthogonal vectors, they will be linearly independent. Okay, yeah, so here is a bit of digression in this proof, but for now, we want to know back to what we want to say now. We want to say yeah, the basis of S and the basis of S perpendicular together will be a basis of Rn. Okay. Yeah, and from this we want to say something. So we want to basically have I guess a more formal way to say this thing. So want to say two set. We want to have two subspace if you take their basis, and these things together become basis of Rn. And the formal way to say this is this direct sum. Okay, so we say U and V are subspace of W, and we say direct sum. Okay, and yeah, so we have W being the big space. So I guess that's a kind of mark W. So W is the bigger space, and U and V are subspace. Okay. So here are W, 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 okay, W, W, okay, and we say, so we want U and V adding together become W, and we write it in this way. So W equal to U O plus V. Okay, so it means we say this is W is the direct sum of U and V, and so this thing basically means that you take a basis of U and a basis of V together become basis of W. And then yeah, so this is the direct sum, and the technical definition is that each thing inside W can be written uniquely as something inside U plus something inside V. Okay, so this is the direct sum, and this proof we need to be very careful. Okay, so basically every word here is important. So this is each, and this is uniquely are important in this definition. Okay, so each means that this U and V together should actually span the whole W, and uniquely means that U and V basically cannot have a overlap. You cannot have yeah, you cannot have something that can be written as something in U and something written as in V. Okay, so they need to be perfectly summed together to W. And yeah, so there are a lot of tricky points about this. So we say U and V together become W, but that doesn't mean W is the union of U and V. And W is the direct sum of U and V. And here is the first counterexample. So we have U, that's the span of E1, so just the x-axis, and V is the YZ axis, and so maybe let's draw this R3 a little bit, okay? So U is the axis, and V is not the YZ axis. V is the YZ plane, and here you see this V equal to U complex complement, orthogonal complement, and they will direct sum together to the whole space. Okay, and yeah, but the thing I want to say here is W is not. W is not U union with V, because say you can have this 1, 1, 0 vector here. That's something in. So you have some vector here inside this xy plane, and it's not in U and not in V. Okay, but it's in linear combination between U and V. It's in this x and this y. Okay, and so this is the first node. And then second note is a bit confusing here, but if we need to, but I want to say about this definition is that in this definition, because you will be talking about orthogonal complement, you might think you want U and V to be orthogonal complement to each other, and that's most of the time you use this definition. But in this definition, we actually didn't say U and V need to be perpendicular to each other. Okay, and in particular, we can have say, well, running out of space. Okay, so we can have U equal to say 1, 0, and I guess 1, 0 is actually not a space. So U is a span. Let's say E1, so, and V can be span this 1, 1, and so it's like this vector and this vector in R2, and but you actually have R2 equal to U direct sum with V by this definition. Okay, because you take the basis of U and the basis of V together, they become a basis of R2. Even though the basis element are not orthogonal to each other, they are still a basis of R2. Okay, and yeah, so that's a bit of a tricky point in this definition. Although we would like U and V be orthogonal to each other, would be nice, but we can also have U and V now orthogonal to each other, and the direct sum still become your whole subspace, whole space, etc. Okay, and yeah, let's see more example. Okay, and yeah, that's a trick point about this definition, and let's see a theorem I want to say. Okay, and we want to use this definition to say more about orthogonal complement. And this is something you might have expected, and now we prove it, is that you have two orthogonal complement, and you take their direct sum, it will become your Rn. Okay, this is a whole space. Okay, and yeah, here is some examples. So if our U is E3 and U is E3 and V is E1, E2, then R3 is a span of E1, E2, E3, and it's a direct sum between U and V. So U is this z-axis, and V is this xy plane. Okay, and but we think about other things. So you have U prime being this E2, E3, this YZ plane, and V prime being this just axis E1, span of E1. Then R3 is now the direct sum between U and U prime. Here we have U prime and V, because okay, so we know saying this each and uniquely are important. Okay, so you think about direct sum between U prime and V, and yeah, it's not. Okay. I guess here we have. Yeah, here we have a very weird definition. We didn't actually define what's the direct sum of everything. Yeah, it's a bit of weird definition here because we cannot take any subspace, any two subspace and take their yeah, here is the weird part of this definition because we cannot take any two subspace and take their direct sum because if this uniquely condition here is not satisfied, then the direct sum doesn't exist by this definition. Okay, so only when this unique condition satisfied, so basically the two subspace have a trivial overlap, we have this direct sum defined. Okay, and yeah, so here is an example of the direct sum not true by our definition. So if we take this u prime and v, then because u prime and v has non-trivial overlap on this E2, so actually by our definition, R3 is not a direct sum between u prime and v. Okay, so this is a weird part of our definition. Even though you take this basis and this basis together, they will span the whole R3, but you take those two bases together, they are not a basis because you have too many E2 inside. Okay, this is a weird part about this direct sum definition. Okay, and yeah, so basically this is unique, and this each correspond to the two part of this basis definition. So unique means that you take the bases together, they need to be Li. Okay. So here we don't want to say. So this unique condition will basically correspond to the condition of basis being Li, and also we want this each condition. So we want each thing inside W can be written as this linear combination, and here we have an example where each condition is not satisfied. So we have u and v prime together doesn't direct sum to our R3 because u only span E3 and v prime only span E1, and then things on E2 are not inside their direct sum. This things in this E2 it cannot be written as a linear combination between u and v prime, and so here we see this each condition corresponding to this union of bases being the span of the whole space. Okay, so you see that this each condition and this unique condition means that the union of bases of these two spaces must be a basis of W. Okay, so I guess this definition also means that the union, I think I spelled union wrong. Anyway, union of bases, and also need a plural form of basis. I think it's SES is basis for W. Okay, yeah, and yeah, that's a lot of interpretation around this definition. Okay, but basically we spend a lot of time to say this thing. We want something is something and another subspace and another subspace. We take the basis of them each, and then we list those basis elements together. They become the basis of Rn. Yeah, and that means our direct sum is Rn. But actually here the definition is abstract. You see that this definition it didn't say anything about Rn. We actually have an abstract definition. We have two subspace of abstract space, and we can say this space W is the direct sum of these two subspace. Okay, and okay, then finally we can prove our theorem. So this is another thing we say about the direction, and then finally we can say our theorem. We have that back to Rn. We have that we have our any subspace, and it's orthogonal complement, and then they will direct down to the whole space. Okay, and as we said, this is basically rewrite the second part of our theorem 5.2.2. Okay, and yeah, let's see the proof. Okay, the proof is by our theorem we have that this thing is by our 5.2.2 we have this is the basis for Rn. Okay, and now we need to check this direction proof. Direction we need to check this each and uniquely. Okay, so we have this basis here, so we can check the each part. So we can, because we already have a basis here, and we take this basis, and then anything inside Rn can be written as a linear combination of the things inside here. And we see this part is inside S, and this part is inside S perpendicular. So we have X equal to something inside S plus something inside S perpendicular. Okay, so we check each part, and we also need to check the uniqueness part. Okay, so we need to say X can be written as some unique combination of something inside S and something inside S perpendicular. Okay, so we do kind of a proof of a contradiction. So we say X equal to some U plus V and some Y plus Z, and so this U and Y is inside S, and this V and Z is inside S perpendicular. Okay, so we want maybe for some different U and Y and V and Z. Okay, and but we want to prove that it's not true. We want to prove U will equal to Y and V will equal to Z. Okay, and yeah, we start with this equation, and we move this part, this middle part, a little bit. Okay, so we have U plus V equal to Y plus Z, and we just move things around a little bit, and yeah, we move things around a little bit. Then move Y to this side and V to other side. Then we have U minus Y equal to Z minus V. Okay, but well, U and Y are both inside S, and V and Z. Sorry, and yeah, oh sorry, U and Y are both inside S, and Z and V are both inside S perpendicular. So this side is inside S, and this side is inside S perpendicular, but they are equal. So we have something both inside S and S perpendicular, and we know from our lemma 0, then this thing must be the 0 vector. So we know the difference between U and Y and the difference between Z and V must be 0, and yeah, U must equal to Y, and V must equal to Z, and so this decomposition must be unique. Okay, so yeah, that's our theorem 5.2.3. Basically says that basically says this thing. So this direction interpretation is the same as the interpretation we said before. This union or basis interpretation. Okay, so you have direction of two orthogonal complement. They must be sum to your full space Rn, and actually, if you think about this proof carefully, you see that this also works for general abstract space. Although we haven't defined the dual perpendicular space over general space, but it should be generalized very naturally. Okay, and yeah, here is once again you use this remark. This part is very useful. We use that if you have two subspaces orthogonal to each other, then their intersection must be just a 0 vector. Okay. And yeah, then finally we prove our Less theorem. So Less theorem, we have this proof that the orthogonal complement of orthogonal complement is back to your original space. Okay. And yeah, we need to prove. Oh, sorry, I write this wrong. So This should be the inclusion sign. Okay. Then we need to prove this in two parts. We need to prove first that we want to prove this thing, those two sets are same, and the usual strategy is we want to prove S is inside this, and this is inside this, and this is inside this. Okay, and the first part is easier. So everything that is we want to prove S is inside the complement of its complement, then we take anything inside S, we will show that it's inside is complement. Okay, that's because S inside S. Then for Y inside S complement, then by definition of this complement, X is perpendicular to Y. Then X is okay. So here is like nested logic. S is perpendicular to everything of S perpendicular, so S inside this S perpendicular. So then we now take a look at all things inside S. Then we see S inside this S perpendicular. Okay, this is quite a mouthful. Okay, and then also want to prove the other way around. So we have something inside this perpendicular. Then we use now we actually need to use our this structure theorem. So we take everything. So we take this thing, everything inside this thing, and we write it as a linear combination between something inside S and something inside S perpendicular. Okay, so we have this U plus V. And yeah, so basically we want to show this V is equal to 0, then our Z will be inside S. Okay, and to show V equal to 0, we take a whole bunch of property we have. Okay, and first V is perpendicular to this U because just U and V are in two subspace that's perpendicular. And also V will be perpendicular to this combination Z because this is perpendicular. This two perpendicular space is also perpendicular to this one perpendicular space. Okay, this is well, a lot of circling around, but in the end we have V is perpendicular to U and V is perpendicular to Z. So we take this equation and inner product with V. And then V inner product with Z will become 0 because this is perpendicular here, and then we write Z as a linear combination here. So this is a V inner product with U, and V inner product with V, and once again V inner product with U is 0 because of this thing, and so this is a V inner product with V. So we see V inner product with V equal to 0. So finally we get V equal to 0. And so everything inside this double perpendicular is just equal to this U, which is inside this S. So yeah, so double perpendicular is inside S, and from those two things we have our result here. Okay, and yeah, so this is a theorem that we say we'll prove. So we have a complement, and they back to your original space. Okay, yeah, so that's the latest hard theorem we want to prove, and for now let's finish, try to, I guess let's take a small review of everything. So we have a whole bunch of concept that introduced. We have this complement concept, and we say complement equal to the original subspace. And we have that complement adding your space or adding sorry, your complement direct sum with your original space is the whole space, and also similar thing, and the dimension also because of that the dimension adding integral equal to the dimension of your space, and also we have this direct sum definition. We have the space is direct sum of two subspace if only if everything inside this space can be written uniquely as the sum of things inside individual subspace here. Okay, So we have a complement, direct sum, and we also have this orthogonal definition. So two subsets are orthogonal if everything inside them are orthogonal to each other. Okay, and we have all those things, and also we have our fundamental theorem. So I think it's around here. Also, we have our fundamental subspace theorem saying that the complement of a row space is the null space. Okay, and yeah, then from our direct sum theorem, we also know that the row space and the null space direct sum together will be the whole Rn. Okay, where n is the number of columns of your matrix. Okay, and yeah, that's a bit of what we will say now. Okay, yeah, so if something, so now we see the orthogonal complement is a symmetric relation. So something is the orthogonal complement of S, then S is the orthogonal complement of T. Okay, and yeah, back to our fundamental theorem, we have that the complement of null is now the row space, and yeah, now the and the complement of null of AT is the column space, etc. Okay, and yeah, and now we can have a bit of corollary. We think about we know AX equal to B is consistent if only if B is inside column space of A. Okay, and but now we can use this decomposition theorem to say use this 5.25 23 to say a little bit about composition of anything inside this any B. Okay, so B can be consistent, or B can be written as something inside column space plus something inside this null space, because null space of A transpose. Okay, because those two are complement to each other, we have this result. So B is either inside this column space, so A is equal to B, or there is some y that's ATY equal to 0, and y and B has a non-zero inner product. And I think it's easier to see in this way. Okay, so we have that the column space of A and the null space of AT are also going to complement to each other. Okay, and now those are vectors inside Rn, and we know that Rn is the direct sum between column space of A and the null space of AT, and so everything inside Rn can be written as some direction on null space of A, or some direction in column space of A. Okay, so yeah, so this is the idea of this theorem. So we can have a B written as a linear combination between its projection on C of A and the projection on null space of A. Okay, and this theorem is saying whether this y equal to 0 or not. Okay, so if y equal to 0, if y equal to 0, then B is then the equation is consistent. B is inside column space of A, and if y not equal to 0, then you have this non-zero y here, and B will have non-zero inner product with y. Okay, so the two cases are y equal to 0 or y not equal to 0. Okay, and finally there's yeah. So any question about this corollary here? So we see that we can decompose any vector inside Rn into into component inside the range of A and the component inside the null space of AT. And we can think so if this component inside null space of AT equals 0, then the equation is consistent. Okay, and yeah, finally we can find our fundamental spaces once again for any matrix. Okay, and now we have one extra fundamental space we would like to find. find a little bit. Okay, so it's this null space of AT that we don't try to find again. Okay, so here we have an example. We find the basis of all those 4 fundamental space. Okay, and now we know. Well, now we know the null space and the current space of AT. Those two are complement to each other, and then this null space of AT and the current space of A complement to each other. Okay, and once again we can find them by Gaussian elimination. So we do Gaussian elimination on A and Gaussian elimination on AT, and from Gaussian elimination of A we can find the basis for row space or the basis for column space of AT, and so these 2 columns should be and also we can find null space of A. Okay, so first we found null space of A. We have this equation, this times something equal to 0. So x1 plus x3 equal to 0, x2 plus x3 equal to 0. We have x3 as a free variable, and we write the x1, x2 as both minus x3. So null space is spanned by this minus 1, minus 1, 1. And the current space of AT, we can just find from here is this 101 and 011 is the basis of the row space of A, and you transpose them is the basis for the current space of AT. And yeah, current space of AT is spanned by those 2 things. And so this and those 2 will become a basis of R3. And similarly, you have the Gaussian elimination for AT, and you get this thing. And so those 2 vectors will become a basis. I guess now we have solved for null space of AT once again. And you want null for this, and yeah, you do a bit of solution. You see that null space is spanned by this thing. Okay, so x1 will be minus x3, and x2 will be minus 2x3. So it's spanned by minus 1, minus 2, 1. And then current space of A will just be spanned by transpose over those 2 things, and it's yeah, spanned by this vector and this vector. Okay. And yeah, you see that this is orthogonal to those 2 vectors, and they together will be span the whole R3. Okay. So yeah, so those the fundamental spaces that correspond to your A. You have current space of AT or row space of A, and null space of A. They are orthogonal complement to each other, and also null space of AT and the current space of A are orthogonal complement to each other. And you can find them by doing Gaussian elimination on A and AT. Okay. And I guess this time we really need to do Gaussian elimination twice, because before we say we can look at the PV row here and here, and so this column and this column together will also span your column space. But you want to find the null space of AT, then yeah, we need to work harder. We need to find we need to basically do this Gaussian elimination here. Okay, yeah, so this is something we have done before, and now we know this result has a bit more structure than we know, because those 2 things are orthogonal complement to each other. Okay, yeah, so that's all we have for 5.2. So we have a whole bunch of definition. So yeah, we see we have definitions. We don't reproduce here, but we reproduce the sign. So we have orthogonal subspaces. They have the notation is x perpendicular 1, means x are perpendicular to each other. And then we have orthogonal complement of a subspace. So we have x, and you give us x orthogonal complement, return us x to the perpendicular sign. And we have fundamental subspace theorem. We have a whole bunch of theorems. So 5.2.1 says that basically n of A equal to R of A orthogonal complement. Okay, this is basically 5.2.1 says. This is a bit of although the logic flow is the other way around, but this is basically the extension of a rank nullity theorem. From here, we see rank nullity theorem actually come from the being orthogonal complement. Although, even though in our proof we go the other direction. Okay, but it's nice to remember that this is related to rank nullity. Okay, then we have direct sum. So we have W equal to some U direct sum V. And from this theorem, we have that a whole bunch of theorem. With this direct sum notation, we have 5.2.2 is I guess 5.2.2 actually don't use direct sum. So 5.2.2 says that let's try to jump back. Maybe here. Okay. So 5.2.2 says that you have S and S dual, and their basis is okay. I guess it's I guess 5.2.2 and 5.2.3 basically say the same thing, but with a different way to say things. So that's just list them together. So these two things are the same way to say that Rn equal to, so the whole space equal to any space plus direct sum of any space with its perpendicular. And 5.2.4 says that this double perpendicular back to your whole space. So yeah, so you take orthogonal complement is so this is a two-side relation. So you take orthogonal complement again, you back to your original space, and so your original space is orthogonal complement to your complement. Okay, and then finally we have this corollary 5.2.45 is a bit disconnected to everything, but they will be, I guess, connection to something we want to say. We have this projection of we can use this kind of rank nullity thing. We can decompose everything inside Rn to be something inside range of A to something inside null space of AT. Okay, and this decomposition thing we will. This decomposition of projection we will talk about more. I think just next section, 5.3, and and let's 1 minute we will have this nice picture that's actually borrowed from UT, and it give you a bit of a cheat sheet on all the subspace we'll talk about. So we have row space, and so we have any n by n vector. We have row space, column space with rank equal to R here, and we also have a null space and another left null space, which is the null space of AT. Okay, and and those two are orthogonal complement to each other, and those two are orthogonal complement to each other. Okay. And so this is our very technical section 5.2, and we'll continue actually next Monday, because Wednesday is a school sports day, so we'll continue on next Monday. On some projection things. Okay, so see you on next Monday. Oh.